Hello. It has been so long since I last streamed. I think it has been a month. I got busy with like freelance stuff and trying to come back. Wait. Let me just set up the chat. And I think last stream I did Newton's method. I learned about Newton's method, but this streams I'm going to revise it and I will do the next chapter. Let me just set up everything first. Okay, now let me change to full screen. Okay, so last stream I did, is it? Yeah, I did L'Hopital's rule and Newton's method. This stream I'm going to revise Newton methods and I'll start antiderivatives. Hopefully the stream after I will do integrals. Let me see if I remember it correctly. So you want to find, if you want to find the root, I'll just do, so wait. So if we want to find the root, we take a random point and we check where it intersects, I think. But there's no root here. Sorry. I'll just do this. Like that. And then take this point. Find the gradient. This is worse. Wait. I don't think this is a good example, but and then that point we find the gradient. I don't think this is a good example. But the point is it's supposed to get closer and closer to this. So yeah, x1 and then gradient x2 and then gradient. We get closer and closer to here. The way we do this is first we choose the first point, just add. So our first point basically is x is 0. I mean x 0. This is our first one. So you want the gradient at let's say this is f of x. You want the gradient at 0. And then this line would be y is equal to this, I think, plus f of x plus, yeah, I guess that makes sense because uh, let me pick another graph. Oops. So if I do take this, which is f x0, and I take a random, let's say x, y, so this gradient is difference in y divided by the difference in x. That is, that basically is this gradient. So we take this formula, put x is equal to 0, I think. No, y is equal to 0, I mean. And then we solve for x, and that becomes our x1. So we do y is equal to 0. Basically, we try to find this point for the new x. And hmm, yeah, x1, and this goes this side. I'm just making sure that what I'm doing is correct. Derivative is equal to x. So when we new, for the x2, we will repeat the same process, but x1 would be here, then x2 would be here. So basically, for the next x, take the previous x minus divided by the derivative. Oops. Then we keep doing that again and again. So why does this not work? At one of the approximation, x and the derivative of f is 0. Oh, so at like, if it's like this, then Newton method would fail. The approximation may approach a different route than the one we are finding. Okay. If it's like the graph is like this and there are two roots, we may be trying to find this one, but we would fail. The approximation may fail to approach a root entirely, or sometimes it might switch. So I think they gave an example here. Where is it? .48. In they say example 4.48. But the point is like there may be a graph. We are using the Newton's method. Like I think it's like this. What if we are finding the Newton methods? Uh, we are finding the Newton method. It brings us to a new x, and then the new x brings us back to the old x. So it's like switching back and forth. Over there, the Newton method won't work. I think they show the example here. Yeah. So x1 and then sends here, and then this goes here. Okay, let's do the questions now. For the following exercises, write Newton's formula for solving f of x is equal to 0. So 407, copy and close. And also I want the answer key. But I don't know what exactly they're asking me to find. This is chapter 4. Four or seven. So 8. So x and well, it's right above. So xn plus 1 is equal to xn minus this xn cubed plus 2xn plus 1, and then the derivative 3xn squared plus 2xn. Is this what they are looking for? E to the power of x. Since the derivative was the same, this and this would cancel out, right? So xn plus 1 would be equal to xn minus 1, I think. Wait, for e to the power of x, we find the derivative, like the updated x would always be going right, and then right. It wouldn't get closer to 0. Oh yeah, there is no root, so I don't think it matters. Mm, 407. Then when these cancel out and become 1, solve using the iteration which differs slightly from Newton's method. Find a C that works and a C that fails to converge, with the exception of C is equal to 0. Okay, what are they asking here? For the following exercises, using the solve f of x is equal to 0 using the iteration. So what I'm supposed to do, so 4 1 1 n plus 1 minus c x square minus 4. And it's not clear what they're asking. So x0 is 0. 0 minus 4c and then x2 is x1 minus c x1 squared minus 4. And then x2 is 4c minus c 4c minus 4. And then this will give 4c squared because 4c and then no wait, minus 4c squared minus plus 4c. It's not clear to me what I'm trying to figure out. And then if we do this, I don't know if I'm doing this correct. Uh, 4c squared. What is 8 times 4? 32 plus 32 is 64. This is cute. Like, I don't know if I'm heading in the right direction. 411. And then plus 4 times 4 is 16. Oh, there's a mistake here. This is x squared. So this would be four c minus I have no clue what's happening. C. Okay, question 143. This I understand. But it's not clear to me what they're asking. So C is 1 over the derivative of this would be 1 over 2x. Okay, I have no clue. Uh, okay, let's try this. But we are supposed to use a computer or a calculator. So x to the power of 4 minus 100 is equal to 0. But can't I just like calculate it manually? X would be like, hold on. So 100 to the power of, that's the root, right? It's plus or minus this. Yeah, but let's say we pick one. Let's say we pick x0 is equal to 4 and let's do this. And the derivative is 4x. So x1 is 4 minus minus 100 and then 4 like that. Wait, hold on. So let's do equal to a x minus minus 100 for x cubed. This is for x cubed. So let's see, x4. Why is it giving an error? Oh, 3.3906. They said 4 decimal places, right? Solve to 4 decimal places using Newton methods. Okay. So now what if I do f and then f again? Hold on. F F F is equal to 3.1625, 3.1625, and then 0.5. How many times? 3 times. Let's do it a fourth time. 1, 2, 3, 4. Three point 1623. Let's do F 6 times. Like, is there an easier way to do the recursive functions? So 3.1623. Now let's do 4, 3, 1. Oh wait, this is different. Okay. I just need to put the x on the other side. So I need to find the value of x where this is 0. So, whoops. So f of x is this. Derivative is low d high minus high d low upon bottom squared. Hold on. This part seems familiar. Let me just try to remember what it was. It was in this. Was it sine 2x? Yeah. Yeah, it is. So x sine 2x upon x square. So uh, minus sine squared x over x. And then I think it's better if I take this and cancel one of the sine x. So x, 2x sine x cos x. I think it's better like this. Is this correct? Really hope this is correct. So x is now x minus sine x. What was it again? Sine x x, 2x cos x. Let me see. Oh, forget this. So f of, let's say, 1. 1 hasn't gotten any closer. Zero point 0.9234. We are not getting any closer. Okay. So I got correct for the first one. For this one, I don't know what's happening. If I say But is this the correct way? That's what I'm wondering. Maybe that's why they asked us to use a computer. If I do sine square x, yeah, the root is at 0. This is going closer and closer to 0. I'm wondering if this is the right way to do it. Okay, let's do the next chapter. Antiderivatives. At this point, we have seen how to calculate derivatives of many functions and have been introduced to a variety of their applications. We now ask a question that turns this process around. Given a function f, how do we find a function with the derivative f, and why would we be interested in such a function? Okay, the reverse of differentiation. At this point, we know how to find derivative of various functions. We know we now ask the opposite question. Given a function f, how can we find a function with derivative f? What? If we can find a function capital F with derivative f, we call f an antiderivative of f. Oh, so this is given the derivative of this is this. We know small f, but we are trying to find capital F. So it's the reverse process basically. So it's not really a one-to-one function. So x square derivative would be to, let's say, x cubed, 3x squared. Now let's say x cubed plus 4. The derivative would still be x squared. X cubed plus some constant c. The derivative will be. So doing the reverse. So if we know this, finding the antiderivative would be this and plus some constant c. For each of the following functions, find all the antiderivatives. So this is x cubed plus c. It's by coincidence. I did not know this example was coming. 1 over x. The derivative of ln of x is 1 over x. So the answer would here would be ln of x plus c. Derivative of sine x is cos x. So the answer here would be sine x plus c. And the for d it would be e to the power of x plus c. Okay. Indefinite integrals. We now look at the formal notation used to represent antiderivatives and examine some of their properties. These properties allow us to find antiderivatives of more complicated functions. I don't like I don't like introducing integrals like this. I think we have to show integrals as like the area under the graph, the sum of the rectangles, and then we show that it's an antiderivative. Okay, so thus far we know that it's reverse. Properties of indefinite. Okay, we can separate it. Sum and differences. Constant multiple. Initial value problem. We look at techniques for integrating a large variety of functions involving products, quotient, and compositions later in the text. Here we turn to one common use for antiderivatives that arise often in many applications, solving differential equations. A differential equation is an equation that relates an unknown function and one or more of its derivatives. The equation is a simple example of a differential equation. Solving this equation means finding a function y with derivative f. For example, the solution are given by 2x cubed plus c. Sometimes we are interested in determining whether a particular solution curve passes through a certain point. Okay. The problem of finding a function y that satisfies a differential equation with the additional condition is an example of an initial value problem. The condition y x0 is equal to y naught is known as an initial condition. Okay, solve this. So so derivative of cos x is minus sin x. So we bring the negative to the other side. Derivative of minus cos x plus sin x. So y is minus cos x plus c. So y, let's just do it like this. y0 is equal to minus cos 0 plus c, and this is 5. So mine, so c cos 0 is 1, right? 6. A car is traveling at the rate of 88 feet per second when the brakes are applied. The car begins decelerating at a constant rate of 15 feet per second squared. How many seconds elapse before the car stops? A car is traveling at the rate. So initial speed is 88. So the car's speed is 88, and then there's a constant deceleration. So acceleration is minus 15 feet per second, feet per second squared. How many seconds elapse before the car stops? Acceleration is S0, sorry, S1 or S0 t. S1 is 0. This is minus 88, negative 15, and then t is 88 over 15, or whatever that is, seconds. How far does the car travel in that time? This is, do I have a calculator next to me? 5.87. Actually, it's repeating 6. So how far does the car travel during that time? How do we figure that out? Hmm. Wait, it's the area, right? The area gives the distance. So 5.86 times 88 divided by 2. think it's this. Yes. Wait, is there another way to derive this other than using the area? I can't remember the formula for. And now we have the exercises. But like when we are learning math, I don't think introducing the indefinite integral here is a good idea. I think we need to see it as a sum. We need to see this as tiny interval of x. Uh, let me tell you. So for summing discrete values, we do something like this. So intervals of x. Here we summing discrete areas. So f of x, let's say it's from this endpoint, f of x times this interval, f of x times this interval, f of x times this interval. Or even let's say it's from this point. So it's basically, so delta x, yeah, never mind. This plus delta times delta x, this times delta x, this times delta x. We are summing up the areas, the approximate. And that's how integrals should be introduced. Integrals should be a continuous version of this. This is discrete, and then this is continuous. So this delta x is now infinitesimally small. That's how integrals should be introduced. And then later on we show that we can solve this by finding the antiderivative. Uh, yes, it was mechanics. Ah, yes, the average velocity. Final plus initial divided by 2. Average velocity is the distance, s is the displacement, divided by time. Is this correct? Is it v final plus v initial? Wait, if the speed, there's a speed here, constant acceleration, and then new speed, then the distance covered would be the area over here, right? So it should be like this is final velocity, initial velocity. So shouldn't it be like this? Shouldn't it be a minus times t? Let me think. I have no clue. No, no, wait. I think I understand. We have to. No, no, I get it. It's this entire area. So it's this plus it with plus it with vi times t, and then together it would be vf plus vi. Yeah, I think I will end the stream here. Next stream I will start learning integrals finally. I'm going really slow. I need to catch up. I intend to finish this book because there are other topics I want to learn as well. So, guess I will see you guys next time.